For this problem, we have snow melting on concrete where it experiences convection from above as well as radiation, and it experiences conduction from the steam pipeline below. So here's our full problem statement. We will begin to solve the problem by considering our radiative heat transfer, and then we calculate our natural convection. So we work through that to find H, and we find our Q from that. And then we consider our snow melt to determine the Q required. And then we set up our resistance network, including the pipe, the ground, the concrete, and the convection of the interior of the pipe. And then we work through that and figure out that our conduction is this, and then we find our pipe depth by iteratively solving. And then for the next part, we just add wind on the upper part and try and find the forced convection heat transfer rate. And we calculate the Reynolds number to get the Nusselt number, find our H, and then find that, and we find it's about 10 times greater. So in this problem, we hit on natural convection, emissivity, resistance networks, external force, and natural convection. Next problem, we consider a copper induction heating coil, and we try to derive the cylindrical conduction equation, and then we apply that to our coil. So first we start with a differential energy balance, and then we reduce our terms, and then we substitute in Fourier's law, and then we take the limit as r approaches 0 to arrive at our conductivity equation. And then we recognize that we're operating at steady state, so we set our time derivative equal to 0, and then we integrate up, solve for our first constant using our first boundary condition of symmetry, and then solve for our second boundary condition of a known external temperature to arrive at our internal temperature. Next up, we have a membrane unit where first we have to calculate the diffusivity of the membrane, and then we try and actually do a unit operation where we try and separate xenon and argon, and we assume that the membrane has a infinite selectivity for xenon. So we just use diffusivity to calculate, and our flux driving force relationship to find diffusivity, and then we calculate our permeability and permeance by multiplying our diffusivity by our solubility. And then from there, we set up our mass balances to determine the concentration of xenon in each solution. And then we calculate our driving force, which is log mean driving force. And then we just back out the area required to actually separate at our desired rate. Next up, we have a two-bank heat exchanger with glycerin flowing through each pipe, and then steam condensing on the outside. So first we need to calculate our heat transfer coefficient in the interior. So that is internal force convection. So we work through the Reynolds number, and we use our Nusselt number correlation. We arrive at H, and then we are given the outer, and then we determine U from our simple relationship. And then we applied the effectiveness NTU method so we can determine the actual temperatures at the end of the pipe. So we calculate our Cmin, and then we calculate NTU, and then calculate our Qmax. And then finally, we can get our actual Q. From our actual Q, we can get our T out. And then for part B of the problem, we go back and verify that our outer convection is correct. So that's a phase change. So we use this relationship, and then we have n equal to 5 because it's 5 tubes tall. And then we get an H that's actually identical to our guess, because to actually solve this problem without an initial guess, you need to iterate. And this is the result of a couple lines of iteration. For our final problem, we have a leak causing a concentration at the surface of benzene. And then over time, this diffuses through, and we're looking at the depth before which our maximum concentration limit is reached. So we consider it as a semi-infinite medium, and then we just have our solved transient mass diffusion equation with the complementary error function. So we can calculate our basically theta term, and then if you have an inverse of the complementary error function, you can solve this algebraically. Otherwise, you just need to do it using Solver or a similar program. And we want these left-hand side and right-hand side to match up. So we iterate through, and we get a value of x of 0.023 meters, which is a bit of an underestimate because in the real world we would have convective forces